We'll see the working of high pass filter. Here also we are seeing the frequency response of a second order Butterworth filter. Since we are seeing the response of a Butterworth filter, the design gain is 1.586, which happens to be in the passband. So we need to keep the input voltage so that output is undistorted. So if I keep the input voltage around 5 volt peak to peak with the gain of 1.586, 5 into 1.586 happens to be within the supply voltage range of your op-amp. If I see the output, which is there connected to channel B, so it's coming out to be around 6.8 volts. So we can ensure that since the gain is close to 1.47 or 1. We'll just take one reading which corresponds to, since my input voltage is 5 volt peak to peak in passband, so what are the frequency we have just kept? The input frequency is around 25 kilohertz from your DSO. Is 25 kilohertz happens to be in the passband of your high pass filter or not? So can we keep frequency anything other than 5 kilohertz, something like 50 kilohertz, 100 kilohertz? So while doing this active high pass filter, which is involving a op amp, you can see we're going to face a problem while finding the passband gain. If I keep the frequency beyond certain range, you can see now I have kept the frequency around 77 kilohertz. You can see the output as distorted. Instead of getting a sine wave, you are having a triangular waveform. Now this is not because of filter, it is not because of RC of the filter, it is because of the op amp. Because op amp will going to have some slew rate, because it has got some slew rate which is not infinite. So we cannot take this 77 kilohertz as your passband frequency. So you are getting a triangular shape of waveform because the slew rate problem of the op amp. So you reduce the frequency such that there is no slew rate effect happening. So even at around 31 or 28 kilohertz, I'm not having any such problem. So let us now measure the passband gain. Now the output voltage happens to be around 6.7 volts. It's around 6.7 volts now. The output voltage is 6.7, the input is 5 volt. We can find what is the gain in the passband. So this V0 is now 6.8. We can find what is the gain of that one, which happens to be 6.8 divided by 5, which is 1.36. So we are designed for 1.56, so we are having a gain of 1.36. so okay, it's fairly good. You can continue with this setup. So we'll slightly, now we need to find the cutoff frequency. So we verified what the passband gain for this high pass filter, which is designed for a cutoff frequency of 5 kilohertz. So as we did it for low pass filter, let us again try to find what is the Lissajous figure of this one. For doing that, let us identify the grounds and have a dot at the center. So let me take the dot to the center. So this is there. Now again, this high pass filter will also give a 90-degree out of phase signal for the two input and output at the cutoff frequency. Release the grounds. You can see since the input frequency is around 28 kilohertz, I'm not having a perfect cycle. So let us reduce the frequency and find out at what frequency this becomes a perfect cycle. So this is there in 200 kilohertz range, and this is the minimum. It's coming out to be 17 kilohertz. Now since we are designed for 5 kilohertz, the cutoff frequency will be close to 5 kilohertz. So I just switched it from 200k to 20k maximum range. Now this is 1 point. Okay, let me again reduce from 20k now. So I'm reducing from 20k. You can see it's coming closer to a circle. So you can find where exactly it becomes a circle. So can we take this as a perfect circle? Okay, this is a perfect circle, which happens to be, you can clearly make out whether they are 90 degree out of phase or not by just releasing the XYA and just pressing both. Can you make out this? Whenever the input is they are at 0. Let me just take this coincide both input output over here, release both of them. When the input or the output is at 0, you can see the other one is there at 90 degree. So this is the zero crossing of one of the waveform. The corresponding other waveform is at 90 degree, which ensures that they are away by 90 degree, which we cannot so easily measure the phase shift here. If I slightly change the frequency here, I don't know by how much it has changed, but using this XYA I can clearly make out the 90 degree phase shift. So if it is there, a perfect circle, now you can see it is not 90 degree. Now it is also not 90 degree. When it becomes a perfect circle, the phase shift will be 90 degree. Now this is the exact 90 degree phase shift, which you can see it in your waveform also. You can see whenever it is crossing 0, you can just coincide this 0 here. Okay, when this crosses 0, you can see there is a 90 degree passing, so which is exactly seen in your XYA. So this is a perfect circle. So this frequency of 4.8 kilohertz, which we can exactly get it from this DSO, which happens to be 4.97 kilohertz, is the cutoff frequency of this high pass filter, which we are designed for 4.9 kilohertz. So this frequency is now equal to 4.97 kilohertz. Now FC is now 4.97 kilohertz. Of course you can find the output voltage here. Output voltage happens to be now equal to, this is there in 1 volt range. Before we measure the output voltage, ensure that your input is there at 5 volt. It is there at 5 volt. Both the amplitudes are there. Okay, let me just take out the output. The input is 5 volt, the output is also 5 volt peak to peak. Gain is 1. So gain is 1 means you can see now you are having the dB of 0 dB. So okay, we'll just verify the gain at two different frequencies, one at the pass band and one at the cutoff frequency. At pass band, which is there at 28 kilohertz, was 2.67 dBs, and at cutoff frequency it is 0 dB. You can see the difference of this gain is close to 3 dB. So that's what you practically get it from the graph. So which we got this from the phase shift of the two waveforms, which happens to be the perfect circle. So we can say that the cutoff frequency of this high pass filter, which was supposed to be 5 kilohertz, is coming out to be 4.97 kilohertz. Now let us find what is the roll off. So to find the roll off, we know that we need to keep the frequency of the input signal in the stop band. So stop band of this high pass filter happens to be less than the FC. So that's why we take 10 times less than the FC. So in your low pass filter, we just made 10 times more than the FC. Now it is 10 times less than the FC. So which happens to be 0.497 kilohertz, exactly 497 hertz. So we reduce the frequency from 4.97 to 497. That we can just do it using this. So you can see now the frequency from DSO is 494 hertz, which is close to the required frequency. Now we need to find what are the output voltage to find the roll off. So let us just find what are the output voltages. This is okay. Before we measure the output, we should ensure that the input voltage is constant there at 5 volt, which is there here. Let us also measure the output. I can say it is a bit distorted in your high pass filter. So you can measure the peak to peak amplitude of this one, which happens to be 2.2 into 50. So that's what is the output voltage amplitude, 2.2 into 50 millivolt, from which you can find the gain, which happens to be 2.2 into 50 millivolt by 5 volt. You can find the gain in terms of dB. You can just name this as G3, this as G2, this as G1. The roll off, which happens to be the slope of the filter, you can just take it around G3 minus G2. So which is ideally happens to be plus 40 dB per decade. So we may get a roll off of around 34 to 36, so which is an acceptable value. Even if it varies up to 32 dB per decade, it is fine, but ensure that you are changing frequency from 4.97 to 10 times less than that. So in this case it was 4.97, that's why we went to 497 Hertz. If it was 4.8, go to a frequency which is 10 times less than that, which is 480 kilohertz. You find out what the output voltage. Before you measure the output voltage, ensure that input is kept at 5 volt peak to peak. You should always use a signal generator which has got less input impedance, which ensures that there is no loading effect on your signal generator. One important point to note here is that while doing the connection, ensure that the ground of your signal generator is connected to the ground of the op amp. So please ensure that if you are not getting the output, first please check the supply voltage of your op amp, whether it is coming as 15 volts or at pin number 7 and minus 15 at the pin number 4. Ensure that you are not missing out this ground connection of the op amp, which you usually miss it out. So this is a common ground. Ensure that that is connected to this ground. So there should be 2 blank wires coming to the ground point. With respect to the ground, we are going to measure all the voltages.